Hello everyone, welcome back to the channel. Today we are going to make this amazing lamp that sucks energy from virtual objects. Spatial computing gets very interesting and exciting when your spatial app is actually interacting with physical objects in the real world. So this app can be an example of how we can facilitate interaction between physical objects in the real world and your Apple Vision Pro app. So in this video, we'll be looking a lot into RealityKit's entity component system to achieve this effect. Things like instantiating particle systems, setting up attractors in particle systems so the particles get attracted towards a point. We are going to take a look at how we can do hand tracking using Spatial Tracking Session. And we are also going to look at how we can set up a Bluetooth peripheral connection on the Apple Vision Pro side so it can communicate with the lamp. We'll also be looking at how to instantiate particle systems and play animations on shaders as well, so we can create the effect of orb disintegrating and the particles kind of getting attracted towards the lamp. So there is this lamp right over here. You've probably seen this guy in some of my other videos. It's usually sitting on top of the shelf. And this is no ordinary lamp. This lamp is a custom lamp that I made, and you can see that at the bottom it has some fancy electronics. It uses a Bluetooth low energy microcontroller by Adafruit, a battery, and there are some wires that are going inside the lamp. And these wires are going to this NeoPixel LED strip right here. So it's just an RGB LED strip. I first want to give you a very high level overview of how this whole thing works. Your Apple Vision Pro app and this lamp communicates over Bluetooth Low Energy. So the Apple Vision Pro sends messages to this lamp's controller, and the controller basically changes the color of the light. So for the setup of like the orbs and stuff, I'm basically randomly placing some orbs in my space. And what I'm doing is I track the distance between the orb and this lamp. And when this lamp gets very close to one of the orbs, it essentially triggers a sequence of animations on the orb. So it will start the disintegration of the orb, it will play an animation to start a particle system, and the particles get attracted to the position of the lamp. So these are the things we'll be doing. As the animation happens, Apple Vision Pro sends a message with the RGB values of the orb to the lamp. So the lamp basically changes the color to the color of the orb, and that's how we achieve that effect. All right, lots of talking, let's jump right into it. Let's begin with creating a new project. Make sure we call it energy sucking lamp. Our initial scene will be window. We are using RealityKit as our immersive space renderer, and our immersive space is going to be mixed. First, let us create our orb. We can do that in Reality Composer Pro project. So we'll go into RealityKit content bundle and then open the package, and that will open the Reality Composer Pro project. You can see that our immersive scene is open over here, and you can see that there is a root object and it has some children. So what we'll do first is to get rid of those. We want to start from an empty scene. Now we'll hit the plus button in the top right corner and add a sphere to the scene. I'll rename the sphere to orb. And I'm not going to change much here, but I'm going to remove the default material on the orb. So I'll just go ahead and delete it. And now what we can do is, since we want to create a shader for this orb, I'm going to create a new material here. So I'm going to hit the plus button at the bottom left, and then I'm going to create a material here, and that will be a shader graph material. I'm going to rename this material to be the orb material. You can select the orb material and then go into the shader graph tab, where you can see the node editor for the shader. So this is what our shader graph is looking like right now. And one thing I need is the emissive color property, which is missing over here. So I'm going to delete the preview surface node and add a PBR surface node here. I'll make sure to connect the output from this node to the custom surface input on the outputs node. One thing we forgot to do is to assign the orb material to our orb. So we'll select the orb here, we'll go into its material bindings in the inspector and then select the orb material over there. So now our material is assigned to the orb. Now let's try to give an emissive color to our shader. So let's pick something and you can see that it's there on the material. So we want to set the emissive color property of the orb in code. So what we need to do is expose the emissive color property. The way we can do that is by adding a uniform input for the color. So we'll go into the uniform inputs and simply add a color 3 float. We'll call it emissive color and we'll simply add it. So now we can use this property to set the color in the shader. I also want to set its emissive intensity separately, so I'll add another property and multiply it. So here I'll create another property called intensity. I'll make it a float. Let's call it, say, emissive intensity. And then I'm going to simply multiply this property with emissive color. So the higher the value, the brighter the light will be. So right now its value is 0, so you don't see anything. So let me just pick an initial color, and when I set it to, let's say, higher than 0, then you can see the color gets brighter. Now I want the orb to look like glass, so I'm going to change its roughness to 0 and it will make it look very shiny. I'll make the base color completely black over here, so there is no influence of the base color. Just the color should just come from the emissive color property. Now let's work on creating the disintegration effect in the shader. So we'll start by creating a noise 3D node. So we'll double click, select noise 3D, and you can see that it requires a position. So let's create a position node here. So that gives us a position on the surface, and we can directly plug it into the position, but let's multiply it by some scaling factor so we can change the size of the noise. So we'll create another uniform input, call it noise scale, make it a float and add it, and we'll multiply it with the position, and this should scale the value of noise. And let's now try plugging in the output of this to opacity, and you can see that we see nothing, and that's because our noise scale is 0. So let's change the noise scale to, let's say, 100, and now you can see that there is this interesting sort of noisy looking disintegrated pattern on the orb, which is a good starting point. So one thing you can notice here, that the edge of the noise is very soft, which is not what I want. I want the edge to be super hard, and the way we can achieve that is by using a step node. So I'm simply going to pass the output of the noise to a step node and then pass the output of the step node to the opacity, and now you can see that we get hard edges instead of soft edges. Now I want to control this property using a float, and I want that float value to go from 0 to 1. So 0 is basically the orb is fully intact, and when it gets to 1, I want the orb to be fully disappeared. So I can do that by adding a new input. I'm going to call it disintegration. I'll make sure that it's a float and add it here. You can influence the noise effect by simply adding this disintegration value to the noise node. So what we are going to do is simply add the disintegration value into the output of the noise 3D node before passing it to the step. And when we do that, we get more control over like how the disintegration value influences how the noise and hence the disintegration on the orb is affected. Okay, now you can see that when I change the disintegration value to let's say 10, you can see the orb is now fully intact. And when I set it back to 0, you can see all the holes in the orb. So what needs to happen is when our disintegration value changes from 0 to 1, it needs to make the orb from fully intact to completely disintegrated. And that's why we need to do some remapping, and we can do that by using the remap node. So let's add that. Okay, so to help you understand this, what the disintegration value is doing is simply when the disintegration is 0, we want the influence of the noise to go down, and when the disintegration value is higher, we want the disintegration value's influence to be or the noise's influence to be higher. So we need to tweak and experiment the output values here. The input is going to be from 0 to 1. The output needs to be tweaked so that it can basically affect the disintegration and hence the noise influence proportionately. So let's play with it. Okay, so on playing with it a little bit, I have realized that when I set the out low to 1 and out high to -1, it behaves properly. So when I set my disintegration value to let's say 0.5, this thing is half disintegrated, and when I set it to 1, you can see that the orb is fully disappeared. Okay, you can see there is this one issue that even though the orb is fully disappeared, I can still see the reflection on the surface, and we can mitigate this by simply passing the output of the step node to the ambient occlusion. And now you can see that the reflection kind of plays nicely along with the noise. So wherever there are holes, you don't see reflections, and you can simply do that by passing the output of the step node to ambient occlusion. I also noticed one thing, that when my out high was at -1, then the orb was disappearing very quickly around 0.8. So what I'm going to do is I'm going to simply change the out high value to let's say -0.885 maybe, and what that does is like now the orb will mostly disintegrate when the disintegration value is close to 1. Again, these things you just have to play around, experiment, see what works, what doesn't. There are no magic numbers here. That completes our shader. Now what I'm going to do is just make sure that I'm setting the disintegration value back to 0, so our orbs appear intact when they are loaded in the scene. Now let's jump into Xcode and write some code to make copies of this orb, give them different colors, and randomly position them in the user's environment. So I have written this code in the immersive view file. I'm going to walk you through what it does. So first what we do is we simply open our immersive scene, so which is our immersive.usda in our RealityKit content bundle. Then in that we basically find the orb entity. So we have to make sure that the name matches, and when we find it, we simply save it in a state variable. Keep in mind that we are not really adding it to the reality view's content yet. We are simply saving it to the state variable so we can clone it. So to make copies of it, we use this for loop. Now we make copies of the saved orb entity that we have saved in the state variable by using the clone method. We don't need to set the recursive flag to true as our orb doesn't have any children. We'll assign it a name so we can identify it later. And then what we'll do is we'll set a position of the orb in meters here. So I have given it a random range for X, Y, and Z coordinates, and that basically sets a random position for the orb clone. Now what we need to do is we need to assign it a color, and this is where the array defined above, which is an array of UI color, can be used. And here I have basically defined some colors. Now what happens is that we'll pick a color based on our index of the for loop from the array that we have defined for the colors. And then what we'll simply do is we need to basically assign it to our materials property or our shaders property. So we'll simply find the model component, get the materials, and basically cast the first material as a shader graph material, which is the material we created, and then set its emissive color parameter to our color. So one thing to note here is that the color property that we need to set for this shader property is needed to be in UI color, and that is the reason why the array we have defined above needs to be a UI color, because this property here is going to be a UI color property. Okay, we have to make sure that our parameter name, the emissive color, is correct and matches what we have defined in the shader, or we might get some errors. Okay, so just keep in mind that you are setting the emissive color name right here when you're setting the parameter. And then once you have done all of that, you assign the material back to the model component, which sets the color on the orb clone. And then finally, you add this clone to the content of the reality view. Now let's try running this on a device. You can see now that our orbs are spawned at random spots, and they also have different colors. I realized after running this that the orbs were slightly bigger than my taste, so I'm going to make them a little bit small, maybe 5 centimeters. Okay, so now let's first look into how we can track this lamp's position and then basically have the particles from the disintegrating orb get attracted towards this lamp. So I, like a naive approach, kind of started just by doing object tracking. So I used RealityKit's object tracking APIs and basically went through the process of scanning this lamp and then basically importing it using createML and everything. And then when I got it into the app and when I started tracking, I realized that the lamp doesn't get tracked so well. The reason it doesn't get tracked so well is that it's a perfectly symmetrical object. Like this face and this face is very similar. So RealityKit cannot really determine the orientation of this lamp. A lot of the createML object detection stuff also works on like the colors and the patterns that are kind of on the object itself. And because this is a lamp that emits color, the color of the object itself changes. That makes it a really hard object to track. So object tracking was out of the window. It was not really, I was not getting good results of tracking this object and moving. So what I ended up doing, I simply thought, well, the lamp kind of sits on my hand and I can simply track my hand. So I used the Spatial Tracking Session's hand tracking capabilities to basically track my hand position. I created a child entity to my hand anchor entity with a little bit of offset, and that kind of represented where the lamp would be in 3D space. So that's how I am tracking the lamp. I am not really tracking the lamp, I'm just tracking the hand. It's just that my hand, the lamp is basically at an offset from my hand which is being tracked. So that's how we create this effect. So there are two ways to incorporate hand tracking in your Apple Vision Pro project. One is using RealityKit, which is slightly more complicated, and since visionOS 2.0, Apple has given us the ability to access hand tracking data using a spatial tracking session, and it's very easy to set up. So that's what we are going to do here. So I have added the hand tracking code to the immersive view file, and I start by creating a configuration for the spatial tracking session with the tracking type selected to hand, and then I create the spatial tracking session by initializing it here. Now I simply create an anchor entity
and in that anchor entity I simply define that I want a hand anchor which is for the right hand and the location is for the palm. And just like that, it's very straightforward to use Spatial Tracking Session, providing it with a specific anchor entity that you want it to track. Now I want to visualize where this point is, so I'm also creating a model entity and I'm going to generate it as a sphere that is 5 centimeters, and then I'm going to assign it a simple material that is green in color. Let's call it the energy sucker entity here, and then I'm going to set its position to be 0.1 meters in the y-axis so that it's slightly offsetted from my palm of the right hand. And then I'm going to add it as a child to the right hand entity and add it to the reality views content so we can visualize the whole thing. Once we have done that, I'm just going to add a task view modifier to the reality view, and in that I'm simply going to check if hand tracking capability is available. If that's the case, we can simply run the session with the provided configuration. Otherwise, it will simply throw an error that we don't have permissions to access the hand tracking data. Now we have to do one small thing before we get hand tracking to work. We have to go to our apps info plist and simply add another key there for the NS hands tracking usage description. And once you have added a description there, you can access hands data in your app. Now let's try running this. Now you can see that the green sphere here is following my hand. So it's basically tracking my hand, especially the palm joint of my hand. Now we need to implement a system that when my palm gets closer to any of the orbs, we play the disintegration animation, and we'll have to implement a system for that. So let's do that. We'll start in Reality Composer Pro, and we'll start by creating the components we need for the ECS to work. So we'll start by creating a new component. We'll call it the orb component, and I don't need to write component, so I'll just say orb, and it creates a file called orbcomponent.swift. So I'll hit create. Okay. The purpose of adding this component here is simply to identify the orb as orb. Now I'm going to create another component, and I'm going to call it energy sucker component. I'm not going to add the energy sucker component on the orb, but it's just easier to create it in Reality Composer Pro, so I'm just going to remove it from the orb and only have the orb component assigned to the orb. Now let's jump into Xcode, and here you can see that we have created the energy sucker entity previously. Now what we are going to do is we are simply going to assign the energy sucker component to the energy sucker entity. So we can simply do energy sucker entity.component.set, and we can set and by instantiating the energy sucker component over here. You can also see here that the code for the components we just created can be found in the RealityKit content bundle. Now let's create a new file where we'll define our attraction system. We can call this file the attraction system. We'll put all the logic for monitoring the distance between the palm and the orbs here. Whenever the palm gets closer to one of the orbs, we'll trigger a sequence of animations. So I added some code to the attraction system. At a very high level, what this is doing is simply tracking the energy sucker entity, which is basically anchored to the palm of our hand, and all the orb entities. It monitors the distance between them, and whenever the distance is below a certain threshold, 0.6 meters in this case, it will trigger a sequence of animations on that particular orb. Now let us walk through what exactly this code is doing. To conform to the system protocol, a class needs to have an init and an update method, and we'll use the init function a little later. update will be run every single frame. We'll start by creating two entity queries, one to search for the energy sucker component and other for the orb components. We'll basically create this variable that stores the found energy sucker entity, and we'll also have a boolean so that we don't have to keep looking for the energy sucker entity in the update loop once it's found. So in the update loop, what we'll do is, if we have not found the energy sucker in this system, we'll basically call scene.perform query, and here we'll pass it the energy sucker query. And here we'll try to find the energy sucker entity. When it finds it, we'll basically save this to the energy sucker entity variable and set the has found energy sucker flag to true. Once this flag is set, then our system doesn't keep looking for the energy sucker entity every subsequent run of the update loop. Every single run of the update loop, our system has to find all the orb entities. You should notice one thing over here, that here I'm not using the perform query function, but I'm using context.entities matching updating system when function. So when I previously used perform query, what happens is, for some reason the system doesn't update the orbs appropriately, so the animation might not play appropriately. As a solution, I found out that when I use the updating system when rendering flag here, then the entities update very smoothly and the animations don't feel like they're stuck. So make sure you don't use perform query to find orb entities every single run of the update loop. Instead, you can simply use this function. My understanding is that this function forces the system to update each frame when it renders.
Once we find the orb entities in every run of the update loop, we'll simply check the distance between the energy sucker entity's position and the orb's position. And if this distance is less than a certain threshold, in this case it's like 0.6 meters, then we'll simply destroy the orb. Now one thing to keep in mind is that the destroy function will play a sequence of animations. So what could happen is that the orb still exists and the destroy function might be called on the same orb that is supposed to be destroyed multiple times. So the key is, for the orb that is supposed to be destroyed, we should not call the destroy function on it. And the way we enable this is simply removing the orb component from the orb entity. And that's why I'm setting it to none. This ensures that on the next update run, the entity search will not find the orb that is supposed to be destroyed. Now let's take a look at this destroy function. So in this destroy function, what we are going to do is simply get access to the shader graph material from the orb. We can do this by accessing the model component. Then we'll try to get access to the emissive color property in our shader. Now we don't want to use this property or the color that we get from the emissive color property right away, but we'll need it real soon. Now to perform the orb disintegration animation, RealityKit doesn't really provide us a way to animate the shader property directly, so we have to do it manually. Here you can see that I have defined some variables and constants that will let us control how our manual animation will go. So here you can see that I have defined a frame rate of 1/60, so 60 frames per second. I have set a duration that will, so that the animation will run for 2 seconds. What we are doing here is we are simply using the timer.scheduleTimer function, and we are simply running this timer that fires every frame, so 1/60th of a second, and it repeats. So every single time this timer fires, we update the current frame, that will update the progress, and the progress is calculated by current frame over the total number of frames, and then we simply multiply the progress by the target value to essentially get a disintegration amount that kind of ranges between 0 and 1. Then we assign this amount to the disintegration parameter in our shader. Once you have modified the property, please don't forget to assign it back to the model component of the orb. So now in the end, when our current frame
becomes equal to our total number of frames, we simply invalidate the timer from running and remove the orb from its parent, effectively destroying it. Now we are soon going to implement the particle system, but what might happen is that you can destroy the orb and your particle system might not have completed running the animation, so it will abruptly stop the particle system animation, and we don't want that. That's why I have added this timer for 2 seconds before destroying the orb. Now let's try running this. Okay, so when we run this, our orbs are not really disintegrating. Why is this happening? Well, we have not registered our components and our system yet, so let's do that. We can register our system and our components in the file where we have our abstract. In this case, it's going to be the energy sucking lamp app. We just need to make sure that we are importing our RealityKit content here. Now let's run it again. And it works. You can see that as I bring my hand closer to the orbs simply disintegrate. Now let us complete this by implementing the particle system. Alright, we are back in Reality Composer Pro. Now we want to create this effect. As the orb disintegrates, particles that match the color of the orb basically come off of the orb and they get attracted to the lamp and get sucked by the lamp. So for that we need to create a particle system over here, which we can do by hitting the plus on the bottom left corner and selecting particle emitter. One important thing to pay attention to is that the particle emitter is the child of the root and not of the orb. Alright, so I went off camera and I simply set the properties of the particle emitter and I'll walk you through them. Let us look at the emitter tab first. So I have enabled is emitting flag, then I have disabled loop on it. Let me make this slightly bigger. I've set the emission duration to 2 and the speed of the particle emitter is set to 0. Then I've set the emitter shape to be a sphere so that it can match the orb. Then I have changed the emitter shape size to be 0.07 so that it kind of roughly appears around the orb. And now let's look at the particles tab. Here I have simply increased the birth rate and the burst count to be 200. I have disabled the end color. What else? I have added an attraction strength of 0.5 here, and the attraction center is set to 000. Later we are going to change this encode where it will basically get attracted to our energy sucker entity's position. I have also added a very simple custom texture to the particle system here. Now if I play it, this is how it's looking. It's getting attracted towards the center of the orb. Now let's go to Xcode and instantiate this particle system in our attraction system. Alright, so now in our attraction system what we need to do is simply find a reference to the particle emitter that we have defined in our scene, and then whenever an orb is going to be destroyed, we simply create a clone of this particle emitter. Make sure that we are setting the color of the particle emitter to be the same as our orb's color. In the update function, we'll also set the attraction center of the particle system to the position of the energy sucker entity, which is going to be our lamp. We also need to make sure that our instantiation of the particle system is coinciding with the start of the disintegration of the orb. Let's see how it's done. In the init function, I'm going to load the immersive scene from our RealityKit content bundle here, and once the scene is loaded, I save it in immersive content entity. Now after that, I'm simply going to find the particle emitter entity and make sure that this name matches exactly what we have set for our particle emitter over here. So see, here is particle emitter. I have made sure that it's the same name. Once the particle emitter entity is found, I have simply created a variable that stores this main particle entity so we can clone it. Now let's see how we can instantiate this particle system in our destroy function. So previously, if you remember, we extracted the emissive color parameter from our shader, and this is what we are going to use to assign the color to our particle system. Now you can see here I am simply converting this parameter into a UI color in this switch block. And I am doing this because the main emitter's color property in the particle emitter component requires the color to be defined as UI color. Okay, now what we need to do is we simply need to clone our particle emitter that we have kept in the variable of main particle entity. We now add the particle system as a child to our orb so that it is exactly at the position of the orb. Then we set the color to the particle system, and we can do that by getting the particle emitter component from the particle system entity, get the main emitter property and get the color property from it, and simply assign the UI color that we have converted above. Well, you might be wondering that why can't we simply assign the color directly to the main emitter's color property? And you cannot really do this because a color for a particle system can be slightly more complicated. Like for example, it can have a start value and an end value, and it can sort of go gradually between them, and that's why this particular property allows you to assign it in different ways. So if you just simply want to assign a single color, you simply use these instantiation of a constant single and then color, and you can simply pass a simple UI color to it. Once we have done all these changes, we have to make sure that we are assigning the particle emitter component back after we have made the changes to our particle system entity. The last thing we need to do before we run this is simply assign the position of the energy sucker entity to the attraction center of the particle emitter. To do this, we'll first search all the particle emitter entities in our scene by using our particle emitter query. Once we have found them, we'll simply loop over them. Now, we should not have ideally more than 1 or 2 particle emitters in the scene because we are only instantiating them when an orb needs to be destroyed. Once we have done that, we'll simply find the particle emitter component from that entity. Then we'll get the energy sucker entity's position relative to the particle emitter entity, and then we'll assign it to the main emitter's attraction center property. And again, we have to make sure that if we make any changes to a component, we have to make sure that we assign it back to our entity. Now, what do you think? Will this work? Let's test it. And I'll bring my hand close to the orb, and something is off. Why are the particles not getting attracted to my hand? What is wrong here? I know what could be wrong here, and that has something to do with the coordinate space of the particle system. Alright, so to fix this, we need to go into the properties of our emitter of our particle system and enable 2 flags. One is the particles in local space flag, and other one is fields in local space flag. So once we enable, that should fix the problem. Alright, you can see that the particles are getting attracted to where my hand is, and it's working pretty great. Now we really need to work on some of the hard parts of this tutorial, which is basically playing with Bluetooth Low Energy to communicate with the lamp. Okay, so in order to understand how our Apple Vision Pro app communicates with the lamp, you need to understand how Bluetooth Low Energy works. Now, we are not going to go too much into this networking details, but just a high level understanding of it would be helpful. So, our Apple Vision Pro app implements the client part of this, and a client could also be known as a central in Bluetooth Low Energy terminology. The microcontroller implements the server or a peripheral. So a server has multiple services, and a services has multiple characteristics. These are identified by unique identifiers or UUIDs. So in our case, our microcontroller is going to implement a service called UART, and it will have characteristics for transmitting data and receiving data. So the microcontroller I'm using, which is the Adafruit Feather M0 Bluefruit LE, which is quite a mouthful to say, it implements the UART service by default on the Bluefruit LE module. So here on this page in the documentation of the microcontroller, it's defined what are the UUIDs for the service and what are the UUIDs for the characteristics here that we are going to implement in our Apple Vision Pro app. What I want you to pay attention here is basically these UUIDs that I'm going to be using in our Apple Vision Pro app to communicate with the microcontroller, so you don't feel like you don't know where these keys are coming from. Okay, so keep this in mind.
We'll not learn anything about like how to do like the microcontroller programming, but I'll share the code for the microcontroller as well, so you can just like copy paste that if you just recreate the whole setup, and then I'll give you a high level overview of like what the code in the lamp does.
So I've shared the documentation for the specific microcontroller that I have used for this project in the description. If you read this documentation, you'll know exactly how to set up and create this lamp yourself. It goes in great detail on how to implement this whole thing, and also talks about Bluetooth Low Energy, services, peripherals, and all that good stuff. So you can read up about this in great detail if you do this tutorial from top to bottom, and I highly recommend, if you really want to do this, you should definitely read this. This will improve your understanding of Bluetooth Low Energy and how you can use this controller to even make your own game controllers for Apple Vision Pro. I'm using Arduino IDE to install or deploy the code to the microcontroller here, and I'm using the Bluefruit LE library and the NeoPixel library for the LEDs. So the most important part of this code is the loop function, and what is happening over here is that whenever the Apple Vision Pro sends any sort of RGB values, they are read here by the microcontroller in the loop function. So we get separate RG and B values, and then I'm basically passing these newer RGB values into the interpolate color function that basically does the interpolation between the current RGB value and the new RGB values. So you can see that this is essentially an implementation of a lerping function that basically transfers the color from one RGB value to another RGB value. There is nothing too complex about it. There's some setup here to set up like the NeoPixel LEDs, also instantiating the Bluetooth, but that's very straightforward. But the code for the microcontroller is very simple. Alright, we are back in familiar Xcode territory now. So I'm going to copy some files for the Bluetooth implementation that uses core Bluetooth, and then I'm going to walk you through in detail what these files are doing. So the first file here, which is called RealityKit, simply has the constants for the UUIDs for the UART service and the UART transmit and receive characteristics. The second file here is the BLEview model that implements the entire core Bluetooth API to communicate with the lamp. The most important thing here is the CB Central Manager. The Central Manager is what allows us to use the Bluetooth radios on Apple Vision Pro. It is what allows us to scan, discover, and connect to peripherals. So we set this class as the delegate for the CB Central Manager so we can receive the callbacks for Bluetooth related events. The Central Manager did update state callback for the CB Central Manager, can also tell us when the Bluetooth device is enabled, powered on, powered off. So we are curious about when the device is powered on, and whenever that does happen, we'll start the scan to discover our peripherals. If you look at the start scan function, we are basically calling the CB Central Manager scan for peripherals with services, and here we are passing the BLE service UUID, and the BLE service UUID that we are using is for our UART service. So we are only scanning for peripherals that have this particular service, and that is going to be the microcontroller that is on our lamp. Okay, so once our device starts discovering peripheral devices, a cascade of callbacks starts getting fired. So the first one here is the Central Manager did discover peripheral 1, and this gets called whenever our Bluetooth controller discovers that particular peripheral with that service, and once that happens, we are simply calling the connect function to connect to the peripheral and save that connected peripheral in that remote peripheral variable. So once the connection is successful, we get the callback for central manager central did connect peripheral, and it basically tells us which peripheral is connected, and then we can set our peripheral is connected flag to true. We are also stopping the scan because we don't want to detect any more devices because we have already connected. We also make this class a delegate for the connected peripheral, so we receive callbacks for it, and then we also call discover services to do service discovery on this peripheral. On discovering services, the did discover services callback gets fired, and then here we can start discovering the characteristics on that service. So it's a chain of things, and then once we have discovered the characteristics, we're basically ready to communicate with the device. So now here, this is the most important function here that we are going to use to communicate with the lamp. So write to device, we simply pass an RGB value string that is comma separated. So here in this function, we are simply going to check if the peripheral is connected, and if the peripheral is connected, we are going to basically see if the transmit characteristic is set up, and if it exists, we are simply going to convert our RGB string into UTF-8. So we basically encode it and use the peripheral.write value function to transfer the data to the lamp. So now we have created this BLE view model. We need to instantiate it somewhere, and the best place to do that is our energy sucking lamp abstract, and then you will pass this BLE view model into your views as an environment variable. So I have passed this BLE view model to my content view, and the reason I have done this is because I want to check the state whenever this app connects to a Bluetooth peripheral. So I have simply created a circle and set its foreground parameter dependent on the is peripheral connected property of the BLE view model. Whenever that changes, the color changes from gray to blue. So it is basically an indication of whether we have connected to the peripheral or not. So now when your class is initialized and your BLE peripheral is connected, you can simply call write to device and send data to lamp. So we are now in our attraction system, and then in our attraction system we are simply going to write the value to our lamp. And to do this, what we do is we take the color we have gotten from our shader and we are simply going to convert it into a CI color. The reason we want to convert it to CI color is because we can extract the RGB values from it. So separate RGB values is what we want to send. So once we have gotten these RG and B values from the color of the orb, we are simply going to call the write to device function and pass the RGB values casted as integers. So this will be an RGB comma separated string that will then go to the lamp and change the color on the lamp, and that should do it. One final thing we need to do before we run our app is simply add a new key to the app's info plist, and this time we'll add the privacy Bluetooth always usage description key. Now that we'll be testing with an actual lamp, we don't really need to visualize the green sphere that is on our hand. So we don't need a model entity for our energy sucker entity. So what I'm going to do is comment this line and simply add an empty entity as the energy sucker entity. So we can simply keep the lamp on our hand and our hand will be tracked, and we can create the illusion that we initially thought of. And now let's run it for the last time. So the lamp is initialized with the RGB values of 0, 0, 0, and you can see as I approach it to any orb with a specific color, so yellow in this case, it will give off the yellow particles that will be sucked by the lamp. And here I'll bring it to the blue orb. You can see the blue particles and the lamp becomes blue. So it looks very cool, right?
Alright, so that brings us to the end of this video. We learned a lot of new things, specifically around like microcontroller programming, Bluetooth Low Energy, hand tracking, and a bunch of exciting things around RealityKit and animation sequencing. So I hope this was exciting for you. If you liked it, please like the video and subscribe to the channel, and please don't forget to hit the notification buttons. Leave a comment below. I really love reading those and love the fact that you're liking the videos. More stuff is going to come real soon. We are going to dive a lot deeper into RealityKit to create a lot more procedural effects and things like that. Dive into ARKit APIs as well, like object tracking, and do some more interesting stuff. So stay tuned. I hope to see you in the next one. See ya.